session. My name is Scott Schmidt, and I'm an applications engineer at Digi-Key. I'll be the moderator for today's event. Would just like to remind all the viewers out there, if you are interested in a free PSoC prototyping kit, we'll be giving one of those out to everyone that signs up. We'll be presenting a keyword towards the end of today's session, and you'll need that keyword for the registration process. Also, if at any time throughout this session you have a question for one of our experts, you can submit those via Twitter using the hashtag DKHOA. We'll be keeping an eye on our Twitter feed, and we will address some of those questions in the Q&A session of today's event. Joining us from Cypress today, we have Gagan Luthra, who's a product marketing engineer from San Jose, California. Gagan, would you like to introduce the rest of the Cypress crew there and maybe give us a brief overview of what we'll be covering today?
Absolutely. Thanks, Scott. Hi, everyone. I'm Gagan Luthra from Cypress Semiconductor, and I have with us today Kendall Castor-Perry, who is a senior architect in our group here, and he does a lot of interesting designs with PSoC. We also have with us Keith Nikolai, who is a senior applications engineer, and he's involved with a lot of end products and end designs that our customers do with PSoC today. So in today's Google Hangout, we're going to start with a quick overview of the Programmable System on Chip, or PSoC platform. We're going to talk about our latest and current generation architecture, which is PSoC 4. We'll do a brief overview, and then we'll go into some of the development tools and kits around the PSoC ecosystem, and we'll show you how to get started with those and use them. And Kendall will then share some of his experiences in some sophisticated and complex designs that he's done with PSoC. And these are analog-focused design. So if that's something you're interested in, stay tuned, and we'll cover those towards the second half of this presentation. So I'll go over and switch over to my screen share so I can get into presentation mode, and we'll get started. All right, so as I mentioned, we're here to talk about PSoC 4. PSoC 4 stands for Programmable System on Chip Architecture Generation 4, and it's the world's most flexible and lowest power ARM Cortex-M0 based one-chip solution, and it also sells for a single $1, the entire chip. PSoC is a microcontroller-based technology, and it helps you design embedded systems with mixed signal IP that's around the microcontroller. Just a quick review on today's presenters. Myself, Gagan Luthra, product marketing at Cypress, and we have Keith from our systems engineering group, and Kendall from our architecture group. I'll quickly cover the introduction to PSoC 4 in the first 10 minutes of this presentation. Keith will then cover some of the introduction to the PSoC development tools, namely the PSoC 4 Pioneer Kit and the PSoC Creator IDE, or the software tool. And that should be another 15-odd minutes. And then Kendall will cover some of the designs he's done in creating custom analog front ends with PSoC 4. Another about 15-minute session, and then we should have a good 10-15 minutes for audience Q&A. So please put your questions in via the Twitter feed, and we'll pick them up. So PSoC 4 was launched and released to the market last year in 2013, and since then it's got a lot of accolades, and it's got a lot of attention in the industry by some of the industry experts. Some major publications have given us awards for innovative products and chip design of the year, so on and so forth. So it's that validation from our customers who've liked the products that Cypress is putting out today. So I'll get right into the design scenario that some of us engineers face today with embedded systems. One common trend that we're noticing is that today you have the power and performance of 32-bit CPUs, or 32-bit microcontroller cores. The most popular of them being the ARM Cortex-M base, which are supported by the PSoC platform. What's happening is, to draw an analogy, your 8 and 16-bit proprietary MCUs may do the job and still work for you, but the price to performance ratio and power savings is becoming quite that trade-off, and you're much better off going with that 32-bit MCU and getting all the advantages of it. When designing a complete system, a complete mixed signal system, you often have to work with multiple ICs, and these ICs often come from different semiconductor vendors, and then you're faced with the challenge of also interfacing and learning different design tools to create your entire system. Some of the things you have to do is, for instance, you want to take in data from real-world sensors, analog sensors. You need to create some sort of analog circuitry, so you design that using analog ICs and build your circuits around them. You have to select a central device that controls your entire system, which in many cases is the microcontroller. So you go through a device selection process to pick the perfect microcontroller with the right peripherals around it. And then you also do a bunch of digital design if you have to control or digital outputs or communicate with other chips on the system. And then, of course, to tie the whole thing back together and to provide your system some intelligence, your microcontroller then requires firmware development and programming. Now, because you have multiple ICs that you have designed in, you often end up designing a prototyping board, putting all these different chips together, and then doing your test and validation on the prototype. The drawbacks are, of course, any change in any of these stages causes that vicious cycle of design and redesign, and going back and making changes is difficult and time-consuming. And then a lot of the devices around us today are increasingly becoming battery-operated, and since they are not plugged into the wall and running off of smaller and smaller batteries, there's a big consideration on power consumption. It's difficult to achieve the lowest power at the required performance level, and engineers are having to learn neat design tricks to overcome these limitations of power consumption around their systems today. So PSoC 4 is a very unique architecture, and it attempts to solve all these problems. To begin with, PSoC 4 is designed around a 32-bit ARM Cortex-M0 system. In addition to that microcontroller core, it has a whole slew of programmable analog and digital blocks that allows you to quickly upgrade your 8 and 16-bit systems, but also incorporate all these external ICs that you would otherwise buy separately, and you would increase your BOM costs and also cause integration problems at a system level. Our design tool, which is a free software download from our website, PSoC Creator, it simplifies the design and debug of these analog front ends and the digital glue logic around the microcontroller, because you do everything in a schematic-based tool in PSoC Creator, and at the end of the day, all of these analog and digital processing capabilities are built into that single one-chip PSoC. We also offer a lot of flexible power modes with PSoC, 5 of them to be exact, and in these different power modes, various analog or digital peripherals are either available or in sleep, so you get to optimize your system for just the right amount of power consumption. PSoC Creator also simplifies power optimization by providing you very easy-to-use APIs to switch between all of these various power modes. And then the whole concept with PSoC Creator is really to simplify embedded system design, and we'll show you how we do this today with a quick hands-on demo. In essence, at a very high level, we're taking all these sophisticated system functions like CapSense or capacitive touch sensing, as an example, and we abstract these out at a modular level so that the designer does not have to go down to the nitty-gritty details of working with the technology. He just has it available in a high-level block that's easy and simple to use and get started with. So to reiterate, for $1, you can buy the world's most flexible and lowest power ARM Cortex-M0 based single chip solution. This is a architecture overview of what the chip looks like. If you notice on your left side, this is where you have your familiarities or similarities with your ARM Cortex-M0 core or your microcontrollers. You've got that M0 core running at 48 megahertz. You've got the interrupt controllers, flash and SRAM around it, and a clocking and power management system. Full serial wire debug as supported by several ARM devices. But then again, this is where your similarities with the microcontroller begin and also end. Everything beyond that is how PSoC is different from these other technologies. To begin with, in this block on the top middle, you have a set of programmable analog blocks, namely a 12-bit SAR ADC, or an analog to digital converter that has an excellent 1 megasample per second sample rate. Many microcontrollers are featuring ADCs along with them as peripherals. But in addition, PSoC gives you these programmable blocks like a couple op-amps or amplifiers, a couple comparators, and a couple current DACs that together build our CapSense block. All of these blocks can be configured and programmed and used in conjunction with each other to build circuits that create analog front ends. And these analog front ends are important because they allow you to condition your signal before it goes into the ADC. In addition to the analog blocks, we also have programmable digital blocks. You have a couple of usual suspects like the serial communication blocks. How PSoCs are different is you have a general purpose serial communication block that can be configured as an I2C, an SPI, a UART, and it can be configured on the fly. So we've got a couple of these communication blocks in the PSoC 4. We also have 4 timer counter PWM blocks. And as the name suggests, these can be configured in real time, in runtime, as timers or counters or PWMs. We also have Cypress's proprietary universal digital blocks, which are abbreviated as UDBs. These UDBs are really interesting because they are essentially CPLD-based digital logic blocks that can be used to create additional functions or additional peripherals around the microcontroller that you may not get with the standard MCU. For instance, I can use a couple of these UDBs to make a 16-bit timer or to make another I2C interface if I run out of the ones that come with the chip. And then with everything else in PSoC, your programmable interconnect and routing is also extremely flexible, and as the name suggests, is programmable. You get to decide and choose what functions are going in or out of these general purpose I/O ports, and you also have complete flexibility and control over how these various blocks inside the chip are interconnected to each other. So not only do you have these blocks available as individual blocks, you have the ability to use them in conjunction with each other, create circuits out of them, and build intelligent systems. Now, when we talk about designing circuits, and especially analog circuits, the picture on the left with a soldering iron is what most analog designers or engineers think of, because that's how we're used to be developing and designing circuits in the past. What PSoC is trying to do, and does very well, is allowing you to do hardware with the use of software. PSoC Creator is an extremely powerful software tool that's got a complete visual and schematic-driven interface, and it gives you the power of using your mouse and your computer to create analog and digital circuits rather than the mouse. It has advantages because you can go back and rework things and simply reprogram the chip and not having to go back and resolder your development hardware or your prototyping kits and so on and so forth. And we'll see how we do that today in the tool live. Before we start doing that, just a quick PSoC terms that we'll use often enough today that I want to mention them and define them up front. PSoC Creator is our IDE. It's a free download from our Cypress.com website, and it's a common integrated design environment for the entire PSoC platform of PSoC 3 devices, PSoC 4 devices, and our ARM Cortex-M3 based PSoC 5 LP devices. PSoC Creator allows you to do concurrent hardware and firmware design. Not only does it have that schematic view that we'll see in a few minutes today to design your hardware, it also does all of your firmware development like any other IDE. We define this term components All of the analog and digital blocks that you saw inside PSoC are represented inside PSoC Creator as components. These components are essentially thought of as free embedded ICs that get represented by an icon in Creator, and you simply drag and drop one onto your schematic to tell the chip that, hey, I want to use this function, so populate it in the chip. A visual way of thinking about it, or an analogy, is thinking using Lego blocks. If your PSoC silicon or the device was a blank canvas of a switching matrix, you have these Lego blocks called components which offer different functions, and these functions are analog or digital or firmware, and they can be plopped into the chip in your custom way. So you get to decide and define what your chip looks like, what your peripheral set around the chip looks like. Inside the PSoC Creator tool, these components are represented by an icon, like this op-amp right here, and each component has its own configuration tool, which allows you to exactly configure and set up these components. In addition to the configuration tool, each component also has a data sheet, which describes exactly how this particular component works, how it's characterized from an AC and DC electrical characterization point of view. But also, very interestingly, we provide a set of generated APIs, or libraries of C code that you can use in firmware to control these hardware blocks. And that's really the power of PSoC, creating custom hardware, but then controlling all of that hardware with firmware in a very easy way. I also mentioned power or power savings. PSoC comes with 5 very flexible power modes that consume anywhere from the milliamps per megahertz of power consumption all the way down to, often single-digit nanoamps when we're down in the stop mode and consuming very little power, and you have a few resources that are still available to trigger wake up or interrupt functions on the chip. With the use of these 5 different flexible power modes, as we show here in the graph, you can switch between these power modes depending on what your system is doing to reduce your average current consumption down by a large magnitude. And we'll get started with the development tools, and I'll pass it over to Keith here real quick. I want to leave you folks with these few getting started links. To get started with PSoC 4, all you need to do is download the IDE for free from cypress.com/creator. This is the PSoC Creator IDE. The development kit, as shown here on the right side, is called the PSoC 4 Pioneer Kit. It's only a $25 kit, and it can be purchased from Digi-Key or from Cypress directly at this link. It's a very small credit card-sized kit that has a full built-in debugger capability, has a CapSense slider, and a few other neat things. But the coolest part about this kit is that it's form factor compatible with Arduino shields. So we can use the thousands of Arduino shields available in the open market, like this one called the Danger Shield that I picked up from SparkFun. And you can use these in conjunction with this development board, so you don't have to go create your own custom boards for that quick prototyping. You can just go buy a cheap shield, plug it into the kit, and get to your prototype quickly. We also have a Getting Started app note for PSoC 4 available on the website. It's a very well-written and easy-to-read document that gets you started with how to develop with PSoC. And we do a lot of on-site hands-on training workshops all across the world. And if you're interested in attending one of these workshops in person in a location near you, please shoot us an email to training@cypress.com, and we'll get you set up. With that being said, I will pass it over to you, Keith.
All right, like Gagan said, my name is Keith Micklite. I work in the applications group for PSoC 3, 4, and 5. I deal with a lot of end customer designs, and I'm going to walk you through a basic project in Creator, introduce you to the tool, and then show you an example project that we built for the Danger Shield, which you can see on your screen right now. The Danger Shield has 3 sliders, a couple of little mechanical buttons, a temperature sensor, and we just kind of threw together a quick project to show use of a shield with the Pioneer Kit. Let me switch back to Creator.
Yeah. So we'll do this, and you can switch back.
Okay, so I'm going to first walk you through creating your first PSoC project. So here we'll open up Creator. So when you open up Creator, the first thing you're going to see is this start page. And this start page contains a wealth of information. First of all, you have your recent projects. You have links to creating new projects. This Getting Started section is really useful for new PSoC and Creator users. For each one of our PSoC families supported by Creator, we have Getting Started application notes and projects. You can also find example projects for specific components or specific applications, such as temperature sensing here. Also, I want to point out that on the right, this page is updated from the Cypress website, so you'll see all of our new development kits, Creator features, any news about PSoC and Creator will be updated here. Creator also works without a connection to the web, so you don't have to worry about always being connected. So let's go ahead and create our first project. We'll come up here to File, New Project. We're going to be working with the PSoC 4 family. But also here I want to point out that when you create a new project, we have starter designs. So if you say you want to use, for PSoC 4, an ADC with a differential amplifier, or you want to use see how it goes, you can start out with a pre-made starter design. That is also really helpful. We're going to start with just a blank project. We can call it First Project. Creator throws by default in your Documents PSoC Creator folder. So you can hit OK, and we'll, we already created one. First Project 1. So now when we create a project, we're presented with a blank schematic, which can be a little scary because you don't know where to go first, but don't worry, we'll kind of walk you through this. Think of this is where you're going to make your vision come alive. A few windows I want to point out. On the left here, we have our Workspace Explorer. This is where you're going to deal with all of your source code, data sheets, and build results. On the bottom here, we have an output window, which is build messages and a notice list for your warnings and errors. And then on the left here, we can also minimize everything here to only focus on what we really want to see. If you want to bring them back, you hover over it. You can click this pin. But on the right here, we have what really makes Creator powerful, and this is our component library. And so this is where you're going to interface with the chip, and you're going to build a hardware design based on our components that we provide. So the first thing anybody ever wants to do with their new device is they want to blink an LED. And to blink an LED, we're going to need a pin. So the first thing I'm going to do is I'm going to come up here to the search tool, and I'm going to type in, and that gives us all of our components that are related to input and output pins. Now if I'm driving an LED, I just want to go drive it high and low, and so I'm just going to need a digital output pin. So what I'm going to do is I'm going to click on this guy, and I'm going to drag and drop it onto my blank schematic. And now I have a pin. It's called pin 1. And so every component as well has a configuration tool. And to get to that tool, you can either right-click and configure, or we can just double-click on it. It's going to open up this, this configuration window. The first thing I normally do with my instances is I'm going to label this with a name so I can reference this specific pin. So every component on your schematic is a separate instance of that same component. So if you imagine that your part has a number of pins on it, this is just going to represent one pin, and I want to reference it with the name LED. Right now, first, I'm just going to blink it using firmware, so I'm going to turn off my hardware connection. I'm also going to check this option for Show External Terminal, and I'm going to show you what that does for me in a second. Next, I'm going to come to the General tab. This is where I can set my pin drive modes. So if I want to resist a pull-up on this, or if I want to do it open during drives low for something like I2C, this is where I can set all of that up. Right now, I just want to drive out a voltage, so we're just going to say strong drive. I'm going to have my initial state set to low so that the LED starts turned off. I can apply this, and I can hit OK. And so now this is the terminal that we got when I clicked that Show External Terminal. And what's cool about the PSoC, or the Creator schematic, is you can also use it to annotate and actually almost show like a PowerPoint presentation of what's going on. And what we've done is we provided some off-chip annotation components in this component library over here. And so for this, what I want to do is I'm going to drive an LED. So I'll search for LED. And I can drag and drop this annotation component on here. I like my LEDs to be vertical. And now I've got this LED. Now this isn't actually part of the chip. This isn't actually going to cause any code to be built. What this is this is just me showing what I'm actually doing with this pin. And I can connect a wire between here and here, and you'll notice that this is a dotted wire, and that's because this is an external wire to the chip. What else am I going to need? I'm going to need a resistor. So we have a resistor right here. I'm also going to flip this guy and connect him here. And then we're going to want to connect this to ground. And so I can also power. Here. All right, so now that we've got our schematic set up, we have our LED pin and we have our annotation components. I'm going to come back over here to my Workspace Explorer. I'm going to open up what we call the design-wide resources. In here is where you're going to set up clocks, set up your pin assignments, all that kind of stuff. So what I need to do here is I need to assign this pin to a physical. So I want this on P00. And you can see down here that it's put it on P00 in this diagram. One of the cool things is actually interactive, so I can drag and drop this to P07 over here if I wanted to. And you can do that with any pin on here. The blue text is the fixed function, so there's a certain blocks that work better on certain pins, and so this blue text describes what that is. But any generic interface, such as just a pin for driving an LED, can be thrown anywhere on this design. So I'm going to save, I'm going to go back to my top design, and I'm going to generate this application. So I go to Build, Generate Application. And what this is going to do is it's going to generate it's going to produce all of my generated source code. So all of the APIs Goggins told you about, all the setup, now shows up here in my Workspace Explorer. This is the LED, so these are all the header and C files, source files that I got from placing this pin on the schematic. Then what I can do is I can come over here to main, and if I want to blink this LED, I need to write ones and zeros to this. I can say LED write 1, and then you put some delay in here, so I can say C by delay. And there's a number of utility functions that we provide for you within the within Creator, such as delay or power management, that kind of stuff. This takes milliseconds as a parameter. And so now I can blink this on and off. Like that. You can put another delay in there. If you want to find out, it's like CY delay, if you didn't know that was there, if you go to Help, Documentation, System Reference Guide, there is a system reference guide here that contains all of the creator-specific resources that we provide for you, such as clocking, power management, CY delay, that kind of stuff. But this is pretty brute force, just with some code and a CPU. That's not really anything special. So I don't want to do that. I want to do something a little bit more sophisticated. So let's say I want to drive this LED with a PWM. So I'm going to go back to my schematic here. I'm going to open up my configuration tool for the LED, and I'm going to re-click on this hardware connection. Then we're going to come over here to the Cypress components.
Keith, can I stop you there for a second?
Sure.
Your screen seems to be frozen there on a past step. Back before you assigned the pin within the hardware. I'm just wondering if maybe you have a connection issue on your end. Maybe we could possibly log out and log back in. The audio seems to be working fine. We're just stuck on the screen is stuck on the LED with the annotation that you drew.
We try this. Let's stop this. Can you see us on the camera now?
No, we're still stuck on the PSoC Creator screen.
Okay.
Yeah, we can
Leave call and come back.
sure, just rejoin, I guess.
Where is that?
Yeah, that's the.
We'll just try it. Yeah, just try maybe rejoining the session. All right, there we get some video.
Okay. Can you see us on the camera now?
Yep.
Okay. Which one? Which one?
And we got to the step where you were assigning the pin to the actual LED pin.
Okay. Can you see Creator now? Back on the pin assignment?
Yep. And I guess just to reiterate to the viewers that he entered this this tab through the Project Explorer window.
Yeah, correct. So I entered over here in this Workspace Explorer CY Design Wide Resources, and I was able to assign the pin over here in the port. The next thing I did was I went to build Generate Application up here. And now we're going to do this again, but we're going to do this with the PWM. So there's a couple things I want to show you on here. So I can type in PWM. We have a couple different PWMs in here. I'm going to use the UDB based one. So we can come in here. I'm going to open up this configuration tool. I'm going to go a little bit fast here because we're running a little short on time. So if you have questions, you can ask them in the end. There's a couple of things I want to point out. So these configuration tools are pretty cool. So they'll give you an example output, a lot of them, that will change real time when I set different stuff up here. So say I wanted like a larger duty cycle, I can do this. Another really key thing I wanted to show is that our data sheets, you can find them from the data sheet for a component from its configuration tool. You can also right-click on the component and open it up. So when you do, here, this is what you'll get at the top. This is a fully characterized and detailed data sheet for individual components, and the components are a mix of actual firmware and hardware. And so they have the features, all of the input and outputs connections. You can see all of the API, so these are all of the functions that will be generated for your component. And then they also have DC and AC specifications contained in these data sheets, things like power, resource usage, that kind of stuff. So if you want to know more about any given component, right-click and open up this data sheet. Because we're running short on time, I'm just going to leave this one as it is. I will say that, so once we had this connected, the only thing I would need to do is come over here, and for any given component, there's a start function. So we would have like PWM underscore 1 underscore start. And what this would do, I got caps lock on here. One of these functions, and this sets up everything I just put in the customizer. It's going to set up all the registers for me, and it's going to kick off that component. So now we're going to switch over to the example project that I made up earlier. What this project does is it works with the danger shield. There's those 3 sliders. It's going to read in the slider. It's going to send that over to an SPI interface, which is going to interface with the 7-segment display. I can choose which slider based on the mechanical button. And then the other thing that this project is doing is it's reading a temperature sensor. It's modulating a PWM so that as it gets warmer, the PWM gets dimmer, and as it gets colder, the PWM or the LED is going to get brighter. So now we have a little bit more of a complex schematic here, but you can see we're using the same features as I showed you earlier. We have our annotation components, so you can see I'm reading 4 different inputs: the 3 sliders and the temperature sensor. I have an op-amp buffering the temperature sensor input, and I'm reading this with the ADC. So even our most complicated components, like the ADC, also have a configuration tool. And if I open this up, you can see I have options for everything I'd want from ADC. I have my sample rate, my reference setup, special features such as averaging and decimation that we have post-process are all done through this configuration tool. And we have the same data sheet for this component as we did the PWM. We'll come over here, and I've already built this project. Another thing I want to point out is that if you come over here, there's an analog device viewer, and what this is, I need to build this. This is an actual view of our chip, and when you built a project, it will actually populate. So I have an ADC and an op-amp in this project. It will actually populate this, and you can see what connections creators made to make your design possible. And this is actually an interactive tool as well, so you can actually set switches in here and see how that works. So also on this in this project, I have the 3 switches, and I'm debouncing them. This is all done in hardware. This is all in UDBs. Even these logic gates here are done in UDBs. So I can read in the switch state and switch which slider I'm displaying to the 7-segment. And then we have on this page, this time I use a fixed function PWM. because I wanted to place my SPI master and UDB resources. I could have done that the other way too. The SPI master, we have serial communication blocks that are dedicated COM blocks, and I could have put the PWM UDBs. It kind of depends on which features you want and which way you want to go and what resources you have left over. I also have a debug interface, which is a UART, and that's also done in UDBs. So you can take a quick look at the code just to show you kind of how simple it is to do some of this stuff. So these are all these defines. I've just defined things to make the code a little bit more readable, things like my max and min from the temperature sensor. Here are those start functions I was talking about. So this is how I'm starting up all the components you saw on the screen. And I come down here, this is where I'm reading my button state. I'm switching on the state of the buttons to set my current slider, and then I'm also setting which of those ADC inputs I actually want to scan. I come down here and I say if my ADC conversion is done, then I want to check which current channel I've just scanned and update things accordingly. So if my current channel is the slider, all I have to do is write this TX data to the SPI master, and I've updated my 7 segment. Same with the temperature. I do a little bit of saturation, take care of saturation, and then I can just straight write this LED compare to set my PWM value. And this is debug stuff right here, where I'm just outputting the temperature over the UART to make sure I know what I'm doing. Then I have to do a little bit here to manage my analog mux. So the cool thing about Creator, and especially PSoC, is that there's just 1,000 ways to do anything you want. And so say I don't want to have this code to update the mux on my own. Well, the ADC has its own sequencer. And what's really cool when you're developing hardware via software is you can actually do things that you would with normal firmware, such as comment out hardware, which is a pretty powerful tool. So you'll see I can go in here, I can disable this page, and I can enable this page. Now what Creator is going to do with the disabled page is it's actually going to not compile that code. That's not going to be included, but I've kept it there if I want to go back. And now I can switch over to this page where I decided, oh, I didn't need that buffer because the output of my sensor is fine, and I didn't want to manage my mux on my own, so now I'm allowing the ADC to do it. And if I come back in here to main, so Creator also provides these defines, analog mux. So you'll see that was the name of this guy, which was originally disabled. And so once I rebuild this, I'll actually be using this code down here, which I don't have to take care of the analog mux on my own. So I know that was a super fast intro to Creator and all the options we have. If you have any questions at the end, let me know. But we need to turn it over to Kendall to do his example now.
Switch back into PowerPoint briefly. There you go, Kendall.
Hey, right. Let's sit in the driving seat. Hey, everyone. Thanks to Keith for giving us an overview of what you can do really simply with PSoC Creator, and it's impossible to telescope a whole career of designing stuff like this into a 1-hour presentation. But I certainly, when I go to visit customers, do get the pushback that all this kind of simple stuff is very well, but I've actually got some proper problems that I need to solve with this thing. So how can I get from the kind of understanding how the tool works, doing this simple stuff, to actually solving some real-world problems? Naturally, PSoC is great at doing that. You need to get into the way of using it, but the resources on all the different PSoC chips are really good at solving real problems, especially in the industrial signal conditioning space, in the consumer space. Now, we've been talking about PSoC 4 today. That's our, if you like, it's the baby of the family in the sense that it's a small, very low-cost device, and it doesn't have the huge amount of on-chip resources that some of our big guy products do, like the PSoC 5 LP, which have more resources on than you could really possibly wish for in most applications. But even with the modest resources that you would find on a PSoC 4, basically if you're starting out with a 12-bit ADC and some amplifiers, you can do some pretty cool signal processing. and signal acquisition. And the reason is that we built in a lot of useful stuff like hardware averaging, meaning that the CPU doesn't have to work hard to do that kind of thing. And also, and this is one of the key things about PSoC that differentiates it from so many of the other devices out there, there's this really flexible switching matrix on the chip, which we show it as just a little kind of blue box on our block diagram, but it does enable you to do a lot of analog switching on the part without having to have external multiplexers, 4000 series parts, that kind of stuff. And so I just wanted to show you an example of a real project for a sensor company that makes a little bit more use of that kind of thing than our examples have done so far. And this is an example basically for doing two things at the same time. That's measuring a thermistor and being able to infer from that the temperature pretty accurately. I love thermistors. They're a pretty good way of buying accuracy for temperature measurement. And I'll show you how you can get a really good high quality result out of that with very little in the way of resources. In fact, I give an indication there that when we do the 256 sample averaging, we have an equivalent number of bits of around 17 bits RMS on this particular measurement. It's a very stable, very quiet measurement from a real piece of hardware. That's real measured numbers. And here's a schematic you should be able to see on the screen. This is a real PSoC Creator schematic, and there are some elements on here. I know there's a lot to take in, and we're having to rush. But you'll see over on the right-hand side towards the top, the SAR successive approximation register ADC we talked about before, with now quite a lot more multiplexing. You'll see the multiplexing, there's several layers of multiplexing both before and after the two op-amps, and connected to a whole bunch of device pins that connect both to an external feedback network for the amplifier we're using and also to a couple of sensors. Let's try wiggling the mouse, do some of the real live stuff here. There we go. So let's first of all talk about what's happening over here. We've got our thermistor down here, and this is being measured against a precision resistor. And what this particular part of the measurement is going to do is it's going to measure all of these terminal voltages and then do a very simple calculation which extracts from that the equivalent resistance of the thermistor without suffering from essentially any of the noise elements that you get in the system. This is quite a well-established technique for doing this kind of ratio measurement. So you measure a lot of these different points, and when you do the subtractions, things like low frequency noise and offset in the front end get cancelled out. You get a very clean, very accurate measurement. And talking about thermistors, you'll notice over here, this little component here, this is an example of a software component in PSoC Creator. Now what this is it's something which can be configured to suit the particular thermistor you have and put the coefficients into the linearity correction equation for the thermistor, and enables you to get that temperature out with a proven piece of code which is traceable and uses national standards, so you don't need to know anything about extracting the temperature from that thermistor. The whole thing is basically a very precision thermistor to temperature circuit. So that's what's happening over here. And now we're going to talk about the other part of what we're doing on this. Is we've got a strain gauge on here. This particular example was actually made to look at a magnetoresistive bridge, which is they're transducers where the resistance is dependent on an applied magnetic field, and we're going to find these sensors coming up more and more in future things. A lot of manufacturers in the Far East and in Europe and America making sensors like this. Bridge transducers are all over the place, and in a couple of months' time there's an article coming out that I've written with one of our applications guys which really gives an indication of what we can do with it. So we built a demo which uses a front-end gain amplifier, happens to have a gain of 45, to amplify that very small voltage that happens across the bridge when the resistors get unbalanced by some parameter like strain or magnetic field. And this shows the power of the internal switching, because we use a technique called CDS, or correlated double sampling, which enables us to cancel out a lot of low frequency noise and offset voltage effects. So you might think when you buy a $1 product like a PSoC, got amplifiers and converters, you go, yeah, but you can't do anything useful with that. But boy, you can, because if you use the right architecture and topology, you can cancel out a lot of these errors and get really clean results. So again, I name check a number here. We get an equivalent, nearly 15 bits RMS of equivalent noise right at the bridge terminals, which for a part in this class is exceptional. So if I just waggle my cursor again, you'll see here we're using a bridge, and we've got these two inputs. They're going into these multiplexers, and what we're doing is we make one measurement with the bridge connected up one way, then we flip those switches around, make another measurement, you subtract the two of them, and the result is that you subtract systematic errors that would affect both readings, like offset voltage, also a particular phenomena called 1/f noise, which is a low frequency noise thing. And the net result is really excellent performance. So in case you came away from this presentation with the impression that the PSoC is you know, a little bit of a kind of something that you might just use for very simple applications but can't cut it in the complex world, nothing could be further from the truth. PSoC is a serious piece of analog processing hardware, and I speak as someone who had a previous career before I joined the semiconductor industry, working for 21 years doing industrial precision data acquisition, and products, particularly like PSoC, have revolutionized that. So you don't have to have thick data books from the analog companies on your shelves anymore. You can do serious sensor work. And this really helps because we're currently designing in chips like this into smart sensors with various sensor manufacturers. And you know, PSoC, you know, you'll find eventually when you break these things open, PSoC is in a lot of them because the small size and the easy programmability have really dramatically changed the way in which these people are making such sensors. So I think I'm done with my rapid fire presentation of what we can do with it. I think what we'd like to do now is to throw the whole thing over to a bunch of questions, you know, whether they're really simple questions like how do you change the color of a component or complicated ones, just start firing away.
Yeah, first of all, we had a question on whether or not these slides would be available. These slides, the presentations will all be available online at the Digi-Key.com/Cypress HOA. We'll have an attachment there. Also, another question that came in was, does Cypress have any intention of releasing a Cortex-M0 Plus in the near future?
We do not have a Cortex-M0 Plus in the platform today. We do have a Cortex-M0, which is the PSoC 4. We do have a Cortex-M3, which is the PSoC 5 LP. The way the architecture in PSoC is set up is we have an established partnership with ARM and a nice roadmap that we've developed internally, working with ARM, getting on their latest and greatest cores. So while we don't have an M0 today, M0 Plus rather today, we are on the roadmap with ARM and we'll be looking at their latest and greatest offerings.
Okay, we did have a couple of questions regarding the PSoC Creator IDE. First of all, we had a question, is the PSoC Creator Eclipse-based?
So PSoC Creator is a IDE that works on a Windows operating system, and it's a free download from software. In terms of a look and feel, it looks very much like Visual Studio. PSoC, and also develop the firmware generated that particular system you've designed. PSoC Creator also has the ability to just stop at that first part of doing your hardware and then exporting the entire design with all of the libraries and APIs out to a third-party tool like Eclipse or IAR or Microvision, where you can then go continue your firmware development in a tool of your choice that you are comfortable with. So PSoC Creator is not Eclipse-based, but PSoC Creator allows you to export your hardware configuration to Eclipse, where you can continue your firmware development.
And how much does it cost to download PSoC Creator?
PSoC Creator is a free download from Cypress.com.
Okay, great. I did have an interesting question personally regarding these devices, which I found a little bit difficult to answer. I had a customer ask me if they asked me how many UARTs I could fit in a particular device, and they were talking just broad spectrum in a PSoC device. How many UARTs could you fit in that device? I was wondering if you could maybe elaborate on that maybe specifically to PSoC 4 devices, and then just in general, PSoC in general?
Absolutely. So there's two ways to do UARTs on a PSoC. And the same paradigm applies for any sort of digital communication, by the way, or any digital peripheral. So with the PSoC, you get a few fixed blocks, like the PSoC 4 has 2 serial communication blocks. Now each of these 2 serial communication blocks can be configured as a UART. So out of the box, you get 2 UARTs with the PSoC 4. Now in addition, you have these UDBs, the Universal Digital Blocks. You have 4 of them in a PSoC 4. And Keith, correct me if I'm wrong, but I can use 4 UDBs to create a UART, an additional UART function.
Yeah, correct. You can actually do it with those 2 UDBs, depending on if you want.
Sure.
There's a lot of options with the
So
UARTs.
technically, I could create 2 additional UARTs with the 4 UDBs that we have in PSoC. So then suddenly this chip has the ability to do 4 UARTs, 2 from the serial communication blocks, and then 2 additional on the UDB. Now the next question you may ask is, how do I go create these UARTs on the UDBs? Well, Cypress already does that for you in terms of components. The component catalog that you saw on the right side of your tool, we release new components every 8 weeks, and we offer them as free downloads. The UART built on the UDB is one of those components that's available in your catalog, so all you have to do is drag and drop and use that 3rd or the 4th UART in your design. And what's also unique about us releasing new components every 8 weeks is we realize that there's something new we can do with PSoC. We go build it on the UDBs, and we release it to our customers, so it's like teaching a new trick to your old dog. That same $1 chip that you had before can now do more functions, and you got it for free.
So another point along those lines is that in the datasheet there is a resource usage, and so if you want to know how many of any given item you can fit in a PSoC, you can go check the datasheet, and it'll say something like, so each UDB has a data path and 8 macro cells, and it'll say this component takes 16 macro cells in 1 data path. That means you're going to take up 1.5 UDBs. So another way this question's a little bit complicated because that data path that wasn't used can be used for another component. So it's not like one UDB can actually have different parts of 2 components. So it's a little bit of a complicated question to say how much of this can I fit in PSoC, because there's a lot of different ways you can figure out how to fit it in there.
Yeah, that's exactly my mindset on that as well. We had another question coming in regarding CapSense. Just a quick heads up, it looks like our video is kind of frozen on your end again, but we still have audio, so I think that's sufficient for the Q&A session. But regarding CapSense, could you maybe describe how PSoC, how easy it is to use, or could you elaborate on how it's integrated into PSoC 4 specifically, and then broad spectrum again, all the PSoC devices?
So CapSense, if you aren't familiar, is Cypress's technology name for our capacitive touch sensing products. We have a whole set of standalone CapSense controllers that we sell, and we've in fact sold over 1 billion of them in the last half a decade or so. Our CapSense IP, that same CapSense technology that's in our fixed standalone controllers, is built into every PSoC. And it's done the same way as with any other component. So just like you had the PWM component in PSoC Creator or the SAR ADC component in PSoC Creator, you also have a CapSense component in PSoC Creator. If you would like to use CapSense on your PSoC chip in your particular design, you simply drag and drop that CapSense component onto your schematic, double-click the GUI or the configuration tool, and then tell the component that I want buttons, I want sliders, I want to be a trackpad, I want gestures, all these fancy things that you can configure in the component, and then it gives you a set of APIs to use that hardware block. So the short answer is CapSense is built into every PSoC, and to use it, all you have to do is drag and drop that component and then start writing the firmware with the provided APIs.
Yeah, trailing on to that PSoC Creator reference, are the for every component that you have included in PSoC Creator, you have that C API also available to the user. Now, those libraries that you provide, are they royalty free, or is there any sort of cost associated with using them?
The APIs and the components that ship with PSoC Creator are completely royalty free.
So everything's free to use. You have a free download for the software. Could you speak on the price point of the chips themselves at all? I know the PSoC 4s have come out with some very inexpensive solutions.
Right. The PSoC 4 is one of our lowest cost chips. In fact, we have a promotion running through Digi-Key right now on the Digi-Key website, where you can buy the superset part, or which means the PSoC 4 part number with all of the features. And you can buy that in any of the 3 package types available, the QFN, the QFP, or the SSOP, in any quantities, any units, for $1 per piece of silicon. So $1.00 per PSoC 4 device. We also have our 8-bit PSoC 3 devices that have a lot more resources, but the core is a slower 8-bit core. And then we have the big brother, which is the Cortex-M3 based PSoC 5 LP, which again, as Kendall was alluding to earlier, has a lot of features, maybe more than you'd ever need in these types of designs. And depending on what particular part number you go for, these chips are anywhere from $1 to $5 to $10 and so on.
Yeah. I just wanted to riff on the core thing. Actually, we were talking about programmable digital hardware, that kind of thing. The fact that there's so much programmable hardware in PSoC often frees the CPU from having to do stuff that it would otherwise have to do. So people often think, well, I'm going to need a Cortex-M0 Plus or an M4 or something like that, and that's because in their mind they're doing a lot of algorithms and stuff like that by literally bit bashing in the core. Came across a recent example of interfacing to a PWM microphone, where one particular company in the field, they have a library for doing it, which basically involves the Cortex-M4 straining at this maximum clock rate to perform this work, which we can do entirely in hardware in a PSoC 3. So we have an 8051 8-bit microcontroller sitting there doing practically nothing, while we have all the digital hardware doing something it would otherwise take pretty much a whole Cortex-M4 to do. So that gives you an example of the power that you can get from actually having this programmable digital hardware on chip.
Yeah, I couldn't agree more. One other thing, as far as a roadmap or current solutions, is there any sort of wireless solution integrated into a PSoC device or as a supplemental device?
Not today. Cypress, we made a press release last year where we qualified our Bluetooth low energy radio, and a quick Google search will show you that. And we're actively working on integrating our Bluetooth low energy radio with other products, including products in our PSoC line. So stay tuned for some announcements around that in the following months.
Okay. Yeah, I think that pretty much concludes all the questions that came in over Twitter. Did you have any final remarks?
I wanted to mention one thing real quick. For those of you looking to get that free proto kit, it's a small thumb-sized drive development kit for PSoC 4 that plugs right into your USB port. And we're giving away these kits, and if you'd like to get one, the keyword for this Hangout is Creator. Just like PSoC Creator, the IDE, the keyword is Creator. So keep that in mind.
Yeah, that's right. So as Gagan mentioned, the keyword is Creator. So use that to complete the registration process. Just a few closing remarks. I guess the key points to take away in my mind would be, number one, the technology. PSoC in general is very impressive. The precision analog, the programmable digital that comes with it, and then also the built-in capacitive sensing really sets these devices apart, as Cypress really leads the industry in capacitive sensing technology. Second point I'd like to drive home is how easy these devices are to use. The PSoC Creator IDE, not only is it free, but extremely easy to use, extremely powerful, as Keith showed in the demo, and also that pre-written C API available for every component. The last point that I'd like to try to drive home is how inexpensive these devices are becoming, not only from the chip scale perspective, but also the development tools. As we mentioned many times, Creator is a free download, royalty-free C API, and the development boards themselves are very inexpensive. You have that $25 Pioneer kit you can get for the PSoC 4 device from Digi-Key. just go ahead and go to Digi-Key.com, and you can search for CY8C4, and that will give you all the PSoC board devices as well as the development boards that are available for it. If you guys have anything else to discuss, now would be the time. Otherwise, just to remind everybody that the keyword is creator to get your free PSoC prototyping kit. If not, I think that'll conclude today's Ask the PSoC Expert session. Hope everybody learned a little bit about PSoC devices and are interested in using them in your next embedded design. You can find more information on PSoC devices from Cypress.com and just click on their PSoC Programmable System on Chip link for more information. It is readily available and free. So thanks again for everybody that joined.
Thank you.
Thanks, everyone.
Thank you.
Goodbye.